Hi, good morning, good afternoon, good evening, whenever I have you here. Today we're going to do 7.2, chapter 7.2. That is the second chapter on using the rules of implication to do natural deduction. And if we recall, natural deduction is when we're not using a truth table, we're not using Venn diagrams, we're actually trying to show what follows from certain premises. And as I was trying to say last time, but as we also saw in 6.6, these rules of implication that we're learning are really, in many ways, practices that you do all the time. And so in logic, what we're attempting to show is how good reasoning works. And of course, in chapter 3, we were attempting to show how bad reasoning works. And the words that we used for that, especially in deductive proofs, is arguments that are invalid, right? And so what we're looking for here, though, are valid ways of reasoning, right? That is, modus ponens, disjunctive syllogism, hypothetical syllogism, and so on. And in 7.2, what we're going to see is four more, we're going to start to see this below, or I'm kind of moving the arrow over here, are more rules of implication, four more. So we'll have a total of 8 that we study in chapter 7 in terms of the rules of implication, okay, that we use for constructing a proof. So let's go back to this PowerPoint, which I kind of cut off and decided just to go right into the software. These are the strategies we're using last time with modus ponens, disjunctive syllogism, hypothetical syllogism, and so on, for constructing a proof involving those 4 rules. Okay. So, and modus tollens, I'm always leaving that out. So we always begin by attempting to find the conclusion in the premises. If the conclusion is not in the premises, look at the main operator of the conclusion. This will provide a clue as to how the conclusion should be derived. So if you see a wedge, eventually you're going to have to get to a disjunctive syllogism. If you see a horseshoe, well, that might tell you something different, right? It could be that if all the premises involve horseshoes, that you have a hypothetical syllogism coming your way in the conclusion. Good, something cool there. I'll just mark that as red. And then if the conclusion contains, this will provide us a clue as to how the conclusion should be derived. So we're trying to construct ways into the argument. If you remember last time, we went step by step. First by showing what could follow from a set of premises, right? And then the next step was to put in premises that we didn't need to show how we could still derive a conclusion from those premises. And then finally, what we're able to do is work backwards from a conclusion into using 2 or 3 rules of implication to work out how an argument would be deduced. So in any case, here it says, so that's the first thing, is we attempt to find the conclusion in the premises. If we don't, we then look at the main operator. And so basically you concentrate on the letter first, and then the operator. And then what you want to do is see, okay, how do I get to that letter isolated so I know the truth of it, right? Through natural deduction. Secondly, if the conclusion contains a letter that appears in the consequent of a conditional statement in the premises, consider obtaining that letter via modus ponens. Okay? So in other words, if it's in the consequent, it has to be true. Well, it could be false as well. But see if you could find that somewhere in the premises using modus ponens. Thirdly, actually, if the conclusion contains a negated letter and that letter appears in the antecedent of a conditional statement in the premises, consider obtaining the negated letter via modus tollens, right? So if the letter is positive, think of modus ponens, modus tollens, and if the conclusion is a conditional statement, you're likely to have a pure hypothetical syllogism somewhere along the way in building the further premises to get to that argument conclusion. If the conclusion contains a letter that appears in a disjunctive statement in the premises, consider obtaining the letter via disjunctive syllogism. That is, proving that by process of elimination, something is wrong. So those are the 4 types of rules of implication, that is, proper forms of reasoning, that we learned in 7.1. But in 7.2, we're going to learn 4 more. First, and these are longer and a little bit more difficult, just because they are longer, but they are also valid rules of implication. One is one that we saw in 6.6, which is the constructive dilemma. If both P and Q, then if R, then S. Premise 1. Premise 2, P or R, therefore Q or S. And this follows actually from, we can show the proof for this. We saw this in 6.6, right? That how this actually, you can build up to this and show that why it is true. Well, both these statements have to be true, and then we know either one of these is true, and then we know either one of these is true. Okay, so, but in any event, just as in the last chapter, anything could sort of stand in for these letters, right? So this is obviously, this not M is standing in for P, and this N is standing in for the R position, right here, because it's out of order. The S is in the Q position, right? And so on, okay? And then we get the not T. Why? Because not T is the S position here and the S position there. So these are both instances of the constructive dilemma, but you can see how complicated they can get, right? That they could be this long, okay? But don't worry, you'll always have this next to you as you're doing the homework and the exam or quiz. And so you'll be able to look over and see what the form of the argument is, and that's what's important. We're looking for the argumentative form. Does it follow this form? Okay. The second one is going to be simplification. And actually, this is easier. If we know both P and Q, we know that P is true. If P and Q is true, we know that both sides have to be true. Remember from the truth tables, this was the only line where P and Q is true, is where both were true. So we could deduce that P is true. This is known as simplification. So we know not F and something else. We know not F is true. We also know the second part is true. We also know that Q is true. That's another way of simplification. We know M or T, and if S then R, again, we know M or T is true. We also know if S then R is a true hypothetical statement. But again, these are both, if this is true, then this has to be true. And then this is a valid argument structure. Okay, far easier and far fewer letters than the constructive dilemma. Okay. Now we get to conjunction. My apologies. Conjunction. This one is fairly simple too. Remember, P and Q has to be true. So if we knew P is true, we know Q is true, then we know P and Q is true. And again, these stand up in that position, right? Not E is in the P position, not G is in the Q position, not E and not G. And again, you can get much more complicated, right? But they are all following this form, right? So we remember from truth tables that P and Q is true if P and Q are true. And so this deductively follows, okay? And so, again, this one I think is rather straightforward. I don't want to say easy because I think reasoning at this level, as you're learning to do, is never simple or just straightforward, especially when we get into natural deduction and applying it. But we need to know these rules of implication. Okay. Secondly, we get the rule of addition. And this one is a little bit trickier or funnier. We know if P is true, then P or Q is true. Remember that P or Q just needs to be true if one side is true. And this is just saying, well, one side is true, then we could just add an or to it, or Q, and that is true as well. So if S is true, then S or not T is true. And it may seem odd that we would need to say this, but this will actually prove helpful when we're looking at rules of implication, right? So if I say I'm going to the bar, then the statement, if I'm going to the bar, either I'm going to the bar or I'm quitting smoking is true, right? Anything could stand in there. Or I'm quitting driving, or whatever. Doesn't matter. As long as one side is true, the disjunction is true. So this is sort of the opposite of a disjunctive syllogism. It's not a process of elimination, it's a process of addition. Okay? So common misapplications we're going to go through, and we're going to go in at the end and we'll gather these common strategies. Okay? So if the conclusion contains a letter that appears in a conjunctive statement in the premises, consider obtaining the letter via simplification. If the conclusion is a conjunctive statement, consider obtaining it via conjunction by first obtaining the individual conjuncts, that is, both sides. So if the conclusion is P and Q, you look for P on its own line, and you look for Q on its own line. If the conclusion is a disjunctive statement, well, see if you can find it via constructive dilemma or addition. In other words, the constructive dilemma, remember, comes with the horseshoe, right, as a conclusion. So that's one thing you might be looking for. But you might also be looking for a disjunctive, not a disjunctive dilemma, but you might be looking for addition. All you need to do is find if one side is true in the above premises, and then addition works. If the conclusion contains a letter not found in the premises, addition must be used to introduce that letter. In other words, you might have, well, we'll see how this works. Okay? And conjunction can be used to set up a constructive dilemma. We'll see how that works as well. Good. And so now let's get into the software. Let's go full screen. And we are in 7, natural deduction, of course. And we're in the rules of implication. Okay. So you're going to see that we're going to have a number of problems there. So this section obviously introduces 4 more rules of inference, right? That is 4 more valid forms of argument, right? We have the constructive dilemma, which we already saw in 6.6. It is abbreviated as CD. If P then Q, and if R then S, P or R is true, then Q or S has to be true. It resembles 2 cases of modus ponens, right? If P then Q, P has to be true. If R then S, if both of these are true, then that is true, okay? The first one says that if we have P, then we have Q. And if we have R, then we have S. The second line says that we have P or R. Thus, in the conclusion, we can have Q or S. Okay? In other words, just one side of this has to be true, and just one side of this has to be true. We know this from this because both sides are true. This is called simplification, which we've seen. It is abbreviated just SIMP. The first line says that we have both P and Q, and from this we conclude that P necessarily follows, right? Remember, if P and Q is true, P is true and Q is true. And so therefore we know that P is true. So again, we know this is valid because we have a true premise leading to a true conclusion, necessarily. So the way the simplification rule is expressed, we are allowed to bring down, this is not true, only the left-hand conjunct. In fact, actually, you can bring down the right-hand side. However, after we introduce the commutativity rule in the next section, which we may not get to, we will be allowed to bring the right down handjunct as well. So you don't need to worry about commutativity or what that means. It's quite obvious that you could switch these around and it wouldn't matter, right? Peter is going to the store and Quentin is going to the restaurant, right? Well, both have to be true, and therefore, if this is true, then Peter is going to the store or Quentin is going to the store. You just need both, right? Both work. Okay? The second rule of inference is called conjunction. It is abbreviated conjunction. P is true. If Q is true, then P and Q would have to be true on a single line. I think that's hopefully straightforward. And the order of the premises doesn't matter, and so the order of which it is combined doesn't matter either. You can have Q and P. It just doesn't matter. Right? Again, we'll see that with commutativity, P and Q equals Q and P. But you know that. Just the same way that Q or P equals P or Q. Obviously, you can't do the same thing with the horseshoe. Okay? Although you can do the same thing with the if and only if, but because that's an equal sign. But we'll get it, we don't need to know that for now. The rule of addition is a bit odd, I'll admit, but if you know that P is true, then you know that P or Q is true, right? So if one is on its own line and we know it's true, then something else can always be added, and this whole statement, P or Q, will be true, okay? Could it be any statement? Yes, and it is very curious, I admit, but the wedge tells us that, right? That P, remember it's P, or so if we know P is true, remember in the truth table for the wedge, all were true except if both were false. Well, we're told that one is true here, so we know at least this is true. Then yeah, you could choose anything else, right? Addition makes sense once you realize the conclusion is a weaker statement than the premise, in a way, right? In other words, this doesn't really add much information, right? This is it's not really weaker. I don't like that formulation as much, but what it tells you less than this is an affirmative statement. This just adds on this or this, right? Good. Note, the new statement must always be disjoined using wedge to the given statement, okay? It can never be used to conjoin a dot. So this is invalid because we don't know what Q is, the truth value. And for P and Q to be true, both sides have to be true, but the premises tell us nothing about that. So don't mistake the and for the wedge. The wedge is the one where you could just add on. The and is where you certainly cannot. So let's start doing some practice problems with this. And again, it's going to be the constructive dilemma that probably gets you. So from D, well, we can only know one thing. We saw in addition, right, that we could have D or whatever. So let's do D or whatever from line 1. Okay? We can't have D and J because we're not told the truthfulness of D or J, right? We're only told if D is true, then what? D or J is true. We're using addition. Okay? Not both J and Q. We know H. What do we know? Okay? What follows from that? Okay? Well, we know the conjunction, right, is that both of these have to be false in order for the not to be true. This is true, so we know both of these are what? Well, we don't know what these are, right? But we know that both of them together could be true. So we don't know anything about what's on the inside, because this could be true and this could be false, making it false, and then this is true, because the negation, we know that H is true. So the only thing left for us to do is actually to combine the whole of them, H and not both J and Q. And there we get this conjunction here. Okay? We just combine both of the premises and with the dot. So this is in the Q position of P, Q, therefore both P and Q. So what conclusion follows from this premise? Okay? Not K and F or N, right? And this is going to be simplification, right? So we know either side will work, as we said. So we know F or M is true, and we know not K is true from simplification. That is, we can just cross the other out because we know both sides, if the whole statement is true, both sides of the and have to be true. And so they've given us not K, but again, if they gave us F wedge M, that would be another alternative. Okay? All right, so that's simplification, right? Again, you just cut out one side and you get the other. So what conclusion follows from these premises, right? Well, we remember the constructive dilemma. Okay, the first and most difficult one. If G then M and if L then T, G or L, well, we need to get to the other letter, right? And so we know it's going to be a wedge, right? And we know it's going to be the second part of this, M and T. So G, remember, the constructive dilemma is the first, what you're looking is the first part of this. Does it come up in the second as a wedge? Yes. Okay, good. Then in the conclusion, you're going to get these two with a wedge. Constructive dilemma. Okay, that's the way to identify it. Okay, if I haven't been clear about that in 6.6. Okay, so constructive dilemma, look for if P then Q, if Q then S, right? And then the first part, right? Q or R, then I think I got that right. P or R, then R or S, right? So then you just look for those positions here. So we know it's M wedge T. We're not going to have an and we're certainly not going to have a wedge. Okay? Sorry, not a wedge, a horseshoe. Okay? This is the constructive dilemma, or CD. And again, just as last time, you're going to write out on each line what the lines and the CD. Usually I put actually the CD first and then the lines, but however you do it, I don't care. As long as you know that it's a constructive dilemma and you've shown why that is the case. So what conclusion follows from this premise? If N, then L. Okay. Well, for right now, we know we're only doing homework on these four premises given here. Constructive dilemma. Well, it can't be that. We don't have any wedges or second premises. We're always going to need one for that. It can't be, well, it could be addition. We could see a wedge, right? Put this in parentheses and then a wedge, something else completely different. If N, then L in parentheses, wedge. Put any letter, A, except for N and L, or A. And so let's see if we have that. Yep, we have something like that. This is addition. S is not used yet. And then we know, we just add on. Any old statement. It's curious, but it is true. Okay? We just add. The reason this is an important one is because this will help you within proofs most of the time. Not just to get to a conclusion, but to add additional premises to get to a conclusion. So what conclusion follows from this premise? Well, not both R and S and T. Well, we can simplify and just say that not both R and S is true, or that T is true, right? Just cutting one out. That would be simplification, right? And we don't have any other line, so we're not going to probably do anything else with this. So not R and S would have to be true. Okay? Just take off one side. So, all right, and then that's my way of saying get rid of this, and there we go. So what conclusion follows from these premises? Okay? Well, we know that both, we know this is true, we know this is true. And so it's not a constructive dilemma. Why? We don't have a line with a wedge. We don't have N then A and G then F all on one line. Now that may happen. You may build that to that in a proof and then use a wedge to use the constructive dilemma. But what we do know is that these two combined, that is in a conjunction, right, are both true. So it's going to be if N and A and if G then F for line 3. So let's see if we got that. We do. If N then A and if G then F. Okay, that's the conjunction. So what conclusion follows from this premise? Not either F or T. Okay, so, well, it is a wedge, so it doesn't tell anything about the truth values of what's in here, right? They could both be false, making this true. One side could be false, one side could be true. So we don't know anything about this, so nothing deductively follows. Remember, we want this to be true, so whatever's in here has to be false. So that's not going to give us much. We don't know what f is. We don't know what t is. We can't guess that. But we could add to it. Maybe we could do that. That is, use addition, not either f or t, or a wholly other letter. Okay? And this, here it is. Notice it wouldn't be this, now that I look down, just to be careful here. You don't just throw them all in parentheses. We don't ever have a wedge that isn't separated out, right? It's not like a comma. You can't have F or T or W. And granted, in everyday English language you can't, but within logic, at least for what we're doing, you don't have that, right? It's not a comma, right? So you'd have to separate that out. It's only between two. So this is nonsensical. This doesn't follow at all. And this does. We just add another letter. It could be a statement of anything, right? So that's the odd part. It could have something completely oddball, right? Not France is in Europe or Transylvania is in Europe. Actually, that doesn't work. So I need both to be false. France is in Asia or Transylvania is in Australia, or whatever. And literally, you can just use the word whatever, or whatever. It doesn't matter, okay? That works, okay? It's simple addition. Just grabbing some sparkling water. Okay, so what conclusion follows from this premise? If G, then N, and K, well, we know from simplification, it could be K, or it could be if, then J. Both of these sides have to be true for this statement to be true, so it follows that if G, then N is true. That's what they're likely to give you, but later on, you should also know that this side could be true. We could just switch these around any way we want. So if G, then N. K is also true. So let's click that. It's gonna incorrect, but we must wait after we have introduced commutativity. You can know that right now, that these are the same. You could switch these around all you want, the same with a wedge. But it's if G, then N, and that one is correct. Okay? But again, K would also be a valid inference from that. So what conclusion follows from these premises? Well, it looks to me like we don't have any wedges. We don't have anything connecting if E then R in any way like modus ponens or modus tollens from the last chapter. And so this would have to be what? Probably conjunction. If E then R and A, that's what naturally follows. Okay? And so we'd have to have that. Lines 1 and 2, conjunction. Right? R and A, that wouldn't make any sense. We don't know what R could be. Remember, for this to be true, it could be if false, then false is true. Right? E could be false, R could be false, and this could be true. We know this from the truth tables. And so we need to just naturally deduce that that it's got to be a conjunction. Okay, sorry, so that one is this one. 1 and 2, conjunction. So what conclusion follows from this premise? R and Z. Now, it could be two things, right? We know that R is true, and we know that Z is true. Okay? But we also know that's simplification, right? So if R and Z is true, therefore R, or R and Z is true, therefore Z, either side. But we also know that we could take this, put this in parentheses, and add a wedge to it, and we could do, therefore R and Z, or whatever, right? That's addition. So let's look down below. These are all additions, so let's make sure we get one that works. R and Z has to be one side, or T. Or T, there we go. Okay, not and. Remember, we can't ever use, even though the word addition does sound like something like a conjunction, and mentally you might confuse that. It's got to be a wedge. It's got to be the V, or as some students call it, right? The V, the wedge, or. Okay? So the conclusion follows from line 1 by addition. Okay, as long as one side is true. So, what conclusion follows from these premises? Well, we see the wedge, and we see this very complicated horseshoe and horseshoe. Well, it's not complicated, but it's with an and. So we know we have constructive dilemma. But we have constructive dilemma a little bit out of order, so just mentally move these, switch these back and around. And remember, the constructive dilemma works by the conclusion. The next line will be n, or what is in the first position, that is the antecedent of both, is or. And then the conclusion will be the antecedent, the consequent of each of the conditional statements. That is the second letter, A before C, antecedent, consequent. So not F or D. Okay, not F or D. So let's see if we have that. We do, and that's our constructive dilemma. Relatively straightforward, even if the premises are not in the order that they're given in the book under constructive dilemma. Okay, and we use line 1 and 2 for that. So let's do some practice problems here. What conclusion can we find from the following premises? And now we're building, right? So we have C or N, and we have W or B. Well, these aren't connected in any way. We don't know the truth values of any of these on their own. So we can't have modus ponens, modus tollens, or anything like that. We can't have disjunctive syllogism because we're not told if one side by process of elimination is wrong. So I think the only relationship between these two is that if we know this is true and this is true, then we know that if we add them both, that both are true by conjunction. And so that is line 1. Either A or B, and either C or N. And we get that from line 1 and 2, right? We don't know anything about W alone. We don't know C and W. That wouldn't make any sense. It has to be the conjunction. Okay? So now let's work some practice problems involving more than 2 lines. Remember, we're building out just as we did in the last chapter. Some of these problems involve rules from the prior section. So we're going to have to use all 8 now. Now I'm sure for the first few, we'll get some help by them just limiting themselves to the 4 that we learned in this chapter. But we need to remember some of these rules may involve modus ponens, modus tollens, disjunctive syllogism, and hypothetical syllogism, okay, from the last section, or all 4 from this section. And so you just need to look at the back of your hardcover to see all 8 rules of implication that we've been looking at, right? Okay, so what conclusion follows from these premises? Okay. Well, let's look. Do we have a connection here? Well, we could combine, put these in brackets and so on, and have a very long one where any of these are combined together. Right? Remember conjunction, if one is true and another is true, we can add them. So we can add all 3, frankly, but we can add just 2 of them. Okay, so that's one. But we could also just simply, what? We know that if one side is true, then the other side is true. We don't know anything about this, right? Although we do know that A is true, we know N is true. Why? Because it's false. For that to be false, this in the parentheses has to be, that this is true, that we know that the and is false, the whole statement, and so therefore A has to be false and N has to be false. Although actually it just takes 1. So we don't know anything about A or N there, but we do know about B. We know that by simplification, we just cut off one side, we get that. That's all that we can gather from that. Okay, so we just take that and we simplify. All right, not S or B, not S. Well, that doesn't give us by disjunctive syllogism anything. Not S, not both S or T. Okay. Well, again, the not S doesn't give us anything. If it was not S, then we would know that B is true. We don't know anything here because we don't know the truth values of anything within to make this not true. Even though not S is true, but this could be, this would be false. This would have to be true. We do know that then T would have to be true of false for this to be true. So we do know something about T, and that's disjunctive syllogism. But that's two of them. But right now I think they're keeping it simple. So we're not going to have two lines down. Not S, we're going to get addition. We could put a wedge of anything else. But it happens actually that T follows from disjunctive syllogism by a couple of lines there. All right, 2. There we go. The conclusion follows line 2 by addition. Okay. That is, you can add anything after a wedge. So what conclusion follows from these premises? If Z, then M and T, not L, not both L, sorry, either L or K, not T, not L. Okay. Well, what can we learn here? Well, we can combine these two, not T or not L. That could be a conjunction. Can we put these two together in any kind of way? No. We could also do addition. We could just add anything, not T or some letter not used, not L or something not already used. Same thing here and on here. But I think it's going to just be this conjunction over here, not L and not T, right? So try not to look at the answers beforehand and use process elimination. It'll be better if you just look inside and see what can be true, right? What can I make of this, right? As I said last time, when we get to proofs that lead to a conclusion, well, not really proofs in the sense of truth tables, but as we do natural deductions and we add premises, add all the ones that you can get on paper first. Okay, so we got now not L and not T. That's 3 and 4, and that's conjunction. Okay, one is true and the other is true. The other has to be true. So, what conclusion follows from these premises? Well, we have the if H and then Q and D then A. Well, we seem to have a constructive dilemma coming our way. Okay. Now, a lot can be said here. We know that both sides of this are true, so if we did simplification, we would cross one of these out and we could have H wedge M, right? Or D wedge A. Okay. We could have the same thing here. Both sides are true. We could have simplification and either side is true. Okay. But it's probably a constructive dilemma, right? We have H or D is true. Then we know that Q or A is true by way of that cross. So that's number 5 is constructive dilemma, and that comes from 1 and 3. Wait, is that correct? Did I do that right? H or D, therefore S or T, and we could have also Q or A. So there are actually 2 constructive dilemmas here given to us because they each have the first as the one that works. Right? This is 1 and 4 by constructive dilemma. Right? I wish I could have gone back and then shown the other one. In any event, they gave you 2, I think, correct answers unless I missed something there. What conclusion follows from these premises? Not J or S. Well, we know from disjunctive dilemma, P or Q, not P. Therefore, Q has to be true. So to this disjunctive syllogism works. We could have these premises added to each other. Not J, if J then S, and all of this in brackets, or and J. That could be true. But let's see what we got here. Can M follow? Yes, that's a disjunctive syllogism, right? We were told that this is not true from line 1, and so 1 and 2 give us disjunctive syllogism. But let's check. Can S be true? We need a few steps to perhaps even get there, but no, that's the short answer. And J and S, we're not told anything about the truth value of S by working from there. Okay, so it has to be M, disjunctive syllogism. Okay. So what premises follow from these? Sorry, conclusion follows from these premises. Right. So remember, we're looking inward, and they're just giving you extra now, right? So this is the same setup as last time in 7.1. They're giving us extra lines to ignore, okay? So we can learn a lot just from what we have here. We know that, well, we don't know much here, right? But we do know that M is true. Well, that still doesn't tell us anything about E and R, right? Because the whole thing could be false. Although E is true, but this could mean that R is true. We're not told anything about that. J wedge H. Okay, so we could also do addition. But we also can just do simple conjunction, E and M. So let's look to the right and see what they have here. E and R. No, we don't know anything about R, right? We don't know anything about E and M. Yes, we do, by conjunction, right? And we don't know anything about the truth value of J. So this is true, and both of them together have to be true. Keep it simple, okay? What conclusion follows from these premises? Well, let's see. Well, we don't have a hypothetical syllogism because these aren't the same. None of these are the same here with the horseshoe. Remember that from last time, right? These aren't both W. These aren't the same either. Good. We're not given any wedge statement. That is, so we're not in constructive dilemma. Let's see. We could get simplification. We know that this side is true, and we know this side is true. So if we're given these in the multiple choice, we could give that. So we know that A is true, for example, by simplification. And there it is, right? There's no hypothetical syllogism in 2 and 3. Why? Because this one isn't even a hypothetical, let alone anything else. So it has to be A, sorry. Follows simply by simplification. Whenever you have an and, you know that one side or both sides are actually true. So what conclusion follows from these premises, right? Either J or T. If either J or T, then M, not J, then M. Okay. So, let's see. Well, we could have a number of different things, but we don't know anything about the truth values in here in a conditional. Even though we're told this is true, false and true could be true. Even though we know this, we don't know anything about T. So we can't get a real disjunctive syllogism, except maybe perhaps by a couple of steps. We could do addition, not J or whatever. All of this in brackets, or whatever. M or whatever. So let's see what they offer us. J or T. No, that's not going to follow for modus ponens. T. No. Not J or S. Are we giving S as any of the letters? Good. Then it's simple by addition. By the way, notice this. It can never be a letter we've already used. Because why? Its truth value might be somewhere tied up in there. So always use a letter. It's always going to be a letter not used yet for addition. Okay. The conclusion follows from line 2. I shouldn't say that's the case. It'll sometimes be the case, but most often in these kinds of questions, it won't be a letter you've seen yet. So what conclusion follows from these premises? If R, then if A, N, then K, N, and R. Okay, well, we know modus ponens, right? If R is true, right? If P is Q is true, if P then Q is true, P is true, then Q is true. Well, this is in the P position. And so we know that if N then K is true by simple modus ponens. We don't know anything about the truth value, though, in here. We're not given anything much to work with. We do know that N is true. Therefore, we would know that K is true, but we'd have to do the modus ponens first to get there. So if N, then K. So we do know, actually, the K truth value. But that's 2 steps, and here we just are doing 1. Modus ponens, and then K, right? So see that? It's in the Q position, and then Q, okay? So knowing this a little bit better, knowing that N is true, then we know that this whole thing has to be true. because if it was false, when R is false, that would make this false. So we know that K then also follows from this. But for right now, they're keeping things simple. So that wouldn't even follow from modus ponens. You have to do something else. If N, then K is simple modus ponens, and that's lines 1 and 3. Okay. So what conclusion follows from these premises? If G, then if S, then N. S, not N. Okay, so a couple things follow. We don't have modus ponens because this isn't in the first place. We don't have modus tollens because we don't have a not on that second side of the conditional. We don't have two sets of conditionals, so they're not hypothetical syllogism. We don't have a disjunct, any wedges, so there's no disjunctive syllogism. So we could have S, N, not N. We can combine two of these lines. Right? And let's see if we have that. Yeah, not S or N. And then, of course, we could have the wedge. S wedge, a letter we haven't used that. S or wedge Z. Right? But this is what's given to us, 2 and 3, conjunction. Right? If S is true and not N is true, not N and S has to be true. So what conclusion follows from these premises? Wow, okay. Well, we know we're going to get a disjunctive dilemma, right? Why? Because we have all the wedges connected by an and we have this. So where does it follow? Okay, so which one is it following? Not F or not J, where it's the first line letter. Oh, yeah, we got the first letter. So we know then, therefore, not W or, with the wedge, not K. Okay, that follows by constructive dilemma, and that is lines 1 and 3. Not W, just making sure, or not K. No, constructive dilemma. Simplification wouldn't work because it's a wedge. It would have to be an and for us to know that not F, and so on. Okay. And so that's straightforward constructive dilemma, even though constructive dilemma is admittedly one of the more complicated of the 8 rules of implication. I think it's the most complicated in terms of the number of letters. So what conclusion follows from these premises? If W, then T. If G, then W. W or G. Okay, well, this isn't a constructive dilemma because we don't have parentheses and the and connecting them. Okay. Well, we do have hypothetical syllogism, so we know if G, then T follows. So let's check to see if that's one of those, and that is. Okay. All right. If G, then T, hypothetical syllogism. Remember that? We take the two, and if we sort of reverse them, but they can be in any order. If the antecedent is the consequent in the other, then it just goes straight forward across. All right. So if Peter is out late, then he won't be able to study for his test. If he doesn't study for his test, then he will not pass the test. If Peter is out late, then he will not pass the test. Right. So that's straightforward hypothetical syllogism. G then T. G then T. Okay. What conclusions follow from these premises? Again, we don't have an and connecting any of the hypotheticals, right? So we can't have constructive dilemma. We don't have a simple A or not one of the consequences, so it's not modus ponens or modus tollens. We could have put these in parentheses and then add on, which would be addition. We could have simplification where it's just one side, right? So, if T, then Z could be one of the answers. And I don't think we can know the truth value of anything else at this point. And there we are. If T, then Z by simplification. Okay, and we only need line 2 for that. What conclusions follow from these premises? If K, then if B, then Q, not Q, etc. Okay. Now, do we have any lineup of the hypothetical syllogism here? No. Do we have a negation of the opposite side? Oh, yes, we do. So we could have not N and S. That would be modus tollens, right? If you just simply reverse this, not Q, then not N and S. Remember, if Peter stays out late, then he will do badly on the test. He doesn't do badly on the test, therefore, modus tollens, he did not stay out late. We know that necessarily by deduction. And so we have that form here, right? If N and S, therefore Q, not Q, therefore N and S, right? Where this is in the P position of if P, then Q, not Q, therefore not P. Okay. The conclusion follows from lines 2 and 3 by modus tollens. So let's find the missing line, right? So we're going to try to supply a missing premise. So this is what they had us do the last time, which I think is one of the better. That is, what do we do? What do we put on line 4 such we could get line 5, right? Okay, and then we'll have to say why. Well, we have a wedge in the background, so that could be addition, but we don't have N simply sitting out there all alone, right? So that's not it. We could have what? We have N or F, so we could have constructive dilemma. So we could have W wedge T here, and that would give us this conclusion. Remember, constructive dilemma, you take the first letter or this letter, and then the conclusion is the second of it. The two consequence with wedges. Okay, so that would be 4 would be W wedge T by way of constructive dilemma. Hopefully you see that. Okay, so that's the only line that I think can be made from that. Sometimes there's multiple answers, of course. If D then N, then Q or Z. If D then N, well we get Q or Z, that would automatically follow. That's modus ponens. We have N, so what do we know? Let's see, well, we don't have a constructive dilemma. We don't have, how would we get to N? Well, we would have to know that N is true to get to D and N. Let's see. Well, we could do this. If we knew that D was true, we would have D and N would have to be true. So that could be one answer. We don't know anything about Q or Z or anything like that to help us really put this in. So I would say put D in here, and then you know N and D is true. Okay. There's nothing else that quickly fits that would give us something. Okay. This is by conjunction. So if we have N is true, D is true, we have D and N. So notice we just completely ignore this because it's not helping us, at least to get to that conclusion. All right. So what premise must you put on line 4 to derive the conclusion by line 5? Okay, if J, then H and I, H wedge I, H and I, then T. Well, let's see. Okay, so if we put, we don't have any knots here in the background, so it couldn't be not T, therefore not H and I, so that's not it. So it's not that. Let's see. If we had J, we could get by modus ponens. If J, then H and I. J is true, therefore H and I, right? So if we had that J is true, we would have a simple modus ponens, right? If P, then Q. P, therefore Q. And this is the Q position. So let's see if we have it. We do. And that's good. All right. Excellent. Okay. This choice gives us a conclusion by modus ponens from line 1. What premise here must you put on line 4 to derive the conclusion from line 5? D if K then M, T wedge, not S, S wedge, not K. Okay, let's see. How do we get there? Okay, so we don't have, I think, addition because K is already here, right? And we're not going to be able to throw something in there that tells us this truth value. But let's see. Okay, so if we threw not T in there, we would know that this would have to be true not S, and so that doesn't help us to get there. Not M would give us K, and then by addition we would know that K or S is true by modus tollens. But that's 2 extra steps because we'd have to do 2 additions. So let's see. So not M does fit because not M then K, but again we need the extra line to do addition. Is it not M? So not M does work eventually. S is true, but we're getting S or K. Not T. Well, that doesn't tell us anything about that. Well, let's see. Not M. This choice gives not K by modus tollens from line 2, but does not give the stated conclusion, right? So we need 1 extra step. We could do addition, right? S wedge K. That is, this is one of those where you can put in any letter. And see how that's going to be helpful? Because eventually you could put these together, so it could be whatever you want, even what letters that are already used. Okay, so that's addition. So we're going to find the missing line again. Okay. Again, when we look at the conclusion, and it's a horseshoe, we tend to think of hypothetical syllogisms. So what would we need? Well, we would need something that crossed over, like if F then J, right? That crossed over with this, because this is if F then J, right? As we have here, we cross out the F's, and then we have if F E then J. That gives it to us right away. We don't need to do anything further. Hypothetical syllogism from line 2, right? And then we put in line 4, and then 5 follows. What premise must be used to put on line 4 to derive the conclusion from line 5? So we have if then, not this, K or R, whatever. Well, disjunctive syllogism we could see from the wedge would give us R. So let's look for where R's are. This isn't going to really help us too much. If we had not K, that would be helpful for disjunctive syllogism. Process of elimination, then R has to be true. If not K was here. Let's see if that's in the list. It's in the list. There we go. That's from line 3. What premise must you put on line 4 to derive the conclusion on line 5? Okay. So we have not C or not both C, sorry, not either or neither C or Q, right? Okay. So, well, one way is modus tollens. If we had not B, that would give it to us, right? If P, then Q, not Q, therefore not P, and this is in the Q position. B, not B, therefore not both, not either C or Q. So not B, that's one thing that we could use to get there. And so let's go there, not B. Do we have it? Yep, there it is. Oh no, I hope I didn't hit anything wrong. Good. It just did something. But that was correct, just to give you the answer. I don't know what I hit, but it's loading. Hopefully I don't have to go back to the menu. Let's just do that. 7. You're in rules of implication. Let's see, what problems were we on? Let's do 32. Find the missing line. It's loading again. Have we seen this one before? Yes, we have. So we're just going to move through these quickly, right? But it's always good to practice again. Again, we just want what gets us to if j, e, then j. Well, we just use this line, and we have if f, then j. We cross out the f's, if e, then j. So if f, then j. Go. We already did this one, I think. If k or r, we just need not k. Right? Disjunctive syllogism. Not b, then not c or b. We did this one already, so there we go. And we use that modus tollens. Okay. So now let's work through a complete proof using these rules of inference. So remember from the last time, if we're given a whole set, we take the conclusion, we put it off to the side. And we may need 2 or 3 rules of inference to get to that conclusion, and wedge B. Okay? And so these are the more difficult ones, but it's like a puzzle. And you're going to now use, probably at the beginning, just the rules of implication we've already learned, but you're going to need to use all 8 rules of inference that we've learned, okay, in order to get here. So we begin by searching for the conclusion in the premises. So how do we know that N or B is true? Okay. Well, we're not given it straight off here, so we're going to have to keep work. We're going to have to do some work. Okay. The conclusion is disjunct statement, of course, and we can do that by addition, right, and by the constructive dilemma, right. But we don't have a constructive dilemma because there's not an and between the two, and so on. Okay, but we may need to get there. So let's keep the rules in mind. So it could be addition, if we get to just n on the table, or b, we can use addition. And if we can get to putting these two together, then we might get to a constructive dilemma. N or B does not appear in the premises, but N appears as the consequent of a conditional statement in line 1, and B appears as the consequent. Remember, consequent is a second in a hypothetical statement of this. This suggests the constructive dilemma is going to get us there. Okay. So to set up the constructive dilemma, you need to obtain the right-hand sides of lines 1 and 2 to get us there. Okay, so we need to show that T or K is true. Well, we know we have T is true, so T or K is going to be true. That is, we can put that as a line, T or K. We can do the same thing for T or R, just by addition. So both are going to be by addition. Right? Again, you could put any letter after that. T or K could be line 5, and T or R could be line 6, all by addition. That'll get us there. And then we can use the constructive dilemma. Okay. We could also do this by, see, this can be done by modus ponens. Let's see, R then, or Q, T. That'll eventually get us there. We'll see there. Okay, that might have to come in between addition. Okay. For line 1, you need to obtain T or K. And for line 2, you need to obtain T or R. And that's easy. We just use line 4 for addition, like I was saying. So we pop those in. Thus, now the proof has been completely thought out. We prove both of these. Then we have modus ponens to get us to here. And those two together give us the constructive dilemma. All right. First, we obtain T or K. Right? That's line 4, addition. Then we do the same thing for line 6, T or R. Okay, well, they want to do this first. We know T or K is true. This is modus ponens. If P, then Q. P, this is the P position, then Q. Okay, good. Next we obtain T or R, but it doesn't matter the order necessarily here. I was just going to do the additions real quick, but they're doing it this way. T or R is true. So line 7 can now be put together with line 2 to give us if Q then B. Right? Why? Modus ponens, if Q then B. Okay. Now we combine lines 6 and 8 to get the constructive dilemma. Okay? Okay, right? So this is conjunction. Just take 6 and 8 and put them together. Then we're going to have, we're going to need, okay, let's do this. And finally, the conclusion follows by 3 and 9. So we have R or Q. What follows? N or B, right? So imagine this right after that, and then you get the constructive dilemma. Okay, so that's one of the more difficult ones you'll get because there's a number of steps. 1, 2, 3, 4, 5 to get all the way down to B. I'm sorry, to the conclusion N or B. Okay, but if we simply combine this, if there's an and, R and or Q, sorry, and R or Q would be the next. We have that. Therefore, N or B would follow. Okay. So here's another example, right? We have F or H, then B and M, B or L, therefore Q and A, F, right? Now we're going to have to look for where Q is, which means we're going to have to know something about B or L, right? And working to there. But in any event, we're looking probably, we have a conjunction, so we could have B and Q. If we get B and Q on their own lines, that would be great. That is, if B is true and Q is true, therefore B and Q is true. We don't have any B and Q in here directly right now, so the others won't work. So it's probably conjunction. Okay, it's not going to be addition because it's not a wedge. So let's keep going. The conclusion is a conjunctive statement. This suggests the conjunction rule, as I was pointing out. B appears in lines 1 and Q appears in line 2. Okay? And so we're going to be using what? Hopefully some modus tollens, right? So we know that a modus ponens, sorry. So your strategy will be obtain each of these letters on a single line, right? That means a line where it's like F, there's just going to be 6 B, 7 Q, what have you, to obtain the conclusion. So B can be derived from the consequent of line 1 by simplification if you first obtain what? F or H, right? But we know F or H is true by addition, so that's going to be line 4. Okay? And then we'll have B and M out of modus ponens. So let's watch. Q can be derived from the consequent of line 2 by simplification if you first get B wedge L. And again, that's going to give us, and you get B wedge L by addition, right? After finding this out, just B or anything, right? And then we could have B and Q. And now we've thought out the whole proof and we just have to write it. Okay? So first you add H to F, right? F wedge H, that's that part. And then we get modus ponens, right? Modus ponens, right? See, this is in the P position. If P, then Q. P, right? Therefore Q, second part, and the consequent. Again, I think when you're doing this on your own, just set out and prove what you can already. And then it'll become clearer. Okay? What can I know already? The 8 lines you can know quite a bit, especially with addition and simplification. All right? Next, take B out of line 5 by conclusion. Remember, we need both. Right? B and Q. Okay, so we need this on its own line. So by simplification, B and M we just get rid of that, and we know that this is true just on its own. Therefore, by addition, by the way, we know if B or L goes on line 6. Why? Because you can add anything. Well, add that. Because now, by modus ponens, we get Q and A. Then we know by simplifying that, again, we're going to, simplifying that, getting rid of the A, we're going to get Q on its own line, and then B and Q will be on their own lines by themselves. Right? So we get Q and B or L, then Q and A is obtained by modus ponens. Right? And then we take Q out of line 8, just so that's by simplification, and therefore we get B and Q on separate lines. I know this looks very complicated, but again, once you have all 8 of these rules, you can do quite a bit. See how much reasoning it took to get there, though? Right? But again, it's a puzzle you're trying to figure out. Right? Sort of like what pieces do I put together in order to obtain these? Okay? I'm trying to figure out a better analogy than a puzzle. Okay? But how do I get to that end line? Okay? Sort of like a maze. Like, how do I get out? Is probably the better one. So we combine 6 and 9 and we get conjunction. Okay, as we've said all along. So that's 10 lines. And we started, I believe, only with 3. So it tells you quite a bit of what we can do. So let's do a practice problem. So before proceeding further, take a moment to find the conclusion in the premises. Well, T and not S. Okay. Well, we have T here, and we have not S here. Well, we know not S is true, and so we just have to prove T. Okay, and T's only given here, so we're going to need to know something about N or C, and if we can get N or C on its own line, then we'll be good. Well, not S on its own line would tell us that N would have to be true by process of elimination, disjunctive syllogism. So we get N is true. Then we do addition. That is, we just add anything to the N now that we know that's true, right? And then we use modus ponens. We get to T. And then we have not S and T both on the same lines. Okay? So what do we write on line 4? Well, let's start with simplification. Right? It's the only one that we could do, at least for now. Can we do N? No, we can't do N. And we can't do, well, we could do N, but we have to get to simplification first. Okay? So the other one we know about, but we're skipping a step. Okay. So once we have not S, what does that tell us? Well, it tells us that N is true. Not S, eliminated, and has to be true by disjunctive syllogism, line 1 and 4. Okay? Okay, so what did we write on line 6? Well, as I said, and I think maybe I was going a bit faster than needed, hopefully by working it out internally. N, okay? Now, we know that we want to get to S, T and S, so hopefully I remember exactly what we needed to do here. Well, we do addition, I think, to get to N or T, so we get to T, and we... and then we would have not S. So let's get to N or C by addition, by 5, right? And that gives us the first part. And then by modus ponens, we get to T. So this one, if N or C, then T, we have N or C, therefore T has to be true, modus ponens. If P, then Q, P, therefore Q. These are in the P position, right? Really need to figure a better way to phrase that. But let's see. We don't need N or Z. There's no addition that we need. We need, sorry, what did I say? 5 and 6, disjunctive syllogism. Where was I going here? If N or C, no, that's not disjunctive syllogism. N or Z, no. T, yes, that's true. Modus ponens, right? 2 or 6. If N or C is true, then T is true. Okay? Modus ponens by 2 and 6. And then we just take these two, 4 and 7, combine them. Not S and T, or T and not S. And then we get 4 and 7 conjunction. Okay? It's not the wedge. Okay, and that's right. All right, the proof is now complete. Why? Because we just needed to get to there. But see how we do 3 or 4 different lines to get there. A lot more reasoning. Okay. Okay, here's another practice problem. We need E wedge H. Okay. All right, so we begin by trying to find these in the premises. Well, we have E here. So if we could show Q is true, then we would get to E, and then by addition we could get to H. That's one way. So how do we just show that Q is true? Right? Let's see. When we have Q here, we have if R then E. We won't be able to get anything out of R alone, right? Because we don't know what G is. So let's see. Let's follow this up and see what we have to do to get there. Okay. So what do we write on line 5? Right? Well, I think first let's do what we know. Right? We have Q here, antecedent consequent. So we, if R then E, 1 and 3 lines syllogism. So we know that. So let's get there. Okay, and see what that tells us if we can put this together with something else. Now let's see. E wedge, right? Well, we have this wedge. Now, what does this wedge tell us? We're either going to have addition or disjunctive syllogism. Those are the only two that give us. So if we get E on its own line, the problem looking above is what? You can't get E on its own line just from working these. You never work out of a conditional to E on its own unless you have one of the other parts of the conditional on its own. We don't, and we don't have a way to get there because you just can't cut off one side. So I would say we're heading straight into the last thing we're going to do is going to be the constructive dilemma, and so we need to construct, right? We have R, then E, and we need to construct how those go together. So R and E, and then one of these to get to E, then E wedge H, okay? So let's do the constructive dilemma. We put 2 together. This definitely follows. R and E is on one line on its own. So 2 and 5 definitely follows. Q, then E, then G, then H. Well, that's true too. Is that going to get us there? No, this is E or H. We're just going to need R or G. So we need R or G, and then we know that E or H is true. So let's do that, and then use the constructive dilemma. Right? We know that E or H is true. By what? We're going to need to put that. R or G is here. Therefore, we know E or H, and that's 4 or 6 is the constructive dilemma. We already have this. If this is true, then this is true. And we're already told that R or G is true on line 4. So we need, E wedge H, which is our conclusion, constructive dilemma. And we're done. And that completes the proof. Okay, again, this is our conclusion written off to the side. Now, by this, we can use what? Well, we know it's addition, so not addition, a conjunction. And so we know that this is, we're going to need S and probably not L on their own line. So how do we get there? Okay, that's going to be the hard part. Well, not L is going to be easy to set up. Why? Because we can get not L by simplification, right? So we have not L. That's good. Process of elimination. Now we have to fix S. By not L, what does it tell us? Okay. Right? Not L is going to give us not J by way of modus tollens. But let's see. Let's start to construct it, and we'll see where we're going. Okay? So what do we write on line 4? All right, well, I would say not L by simplification. All right, you just cut out one side. That's the only thing we know so far. We can't know anything else yet. All right, we don't have a constructive dilemma. We might end up with a, well, let's see. Okay, so we have not L. I don't want to jump ahead too far. What do we know next? Okay, not L is not in the front, so let's go through them all. We can't use modus ponens. Modus tollens would give us not J, and not J would help us what? Well, I say put that down, because that's the one thing we can be sure of so far, is not J. I can't do anything with this yet. I don't know anything about S and P. So not J, let's do that, right? So modus tollens, if P then Q, not Q, therefore not P. If J then L, not L, therefore not J, right? Again, start with what you can prove, right? And that's usually how it's going to work. There's only going to be hopefully just one or two that follow. So not J, they're telling us try again, but I would say put that down. We know that that's true, okay? We know that D is true. Is D going to help us? Well, it does follow from simplification. Oh, sorry, not J modus ponens. There we go. Not J modus tollens. So there we go. I said it out loud. At least you have me on that. But I clicked the wrong one. Okay. So that's another reminder on your test. Be very careful on what you click since you're doing them on computer. All right. So we know not J. Okay. We know these two go together by conjunction, not A and not J, and not J, by conjunction 4 and 5. What does that tell us? Do we know not J or M? We do know this. I would go there. Yes, we could go here. That would be a valid extra step. But once we have not J, we can add or M, because we can add or anything. So using addition, let's go there. Because we get there, then we get to S and P, and then we'll have S on its own line by a simplification, and we already have not L. Okay? So not J or M. Again, P, therefore P or any letter, including M. Not J or M. So the addition one is fantastic for these proofs because in a weird way it feels like imaginary. Like, what, I'm just adding anything? Yeah, just add anything. But you can add what's kind of giving you the answer. Okay? All right, so not J or M, we have that. We know modus ponens, if P then Q, even if it's more complicated. Not J or M is in the P position. We have the P position, therefore Q, S and P. Right? So therefore S and P. Then we're going to have line 8. Right? By simplification, we get S. Right? We need S here. Right? Now, by conjunction, we combine not L and S. And that's your line 9 by addition, right? Addition is never going to be a wedge, by the way. Sorry, conjunction. Conjunction is never going to be a wedge. We have S and not L, okay? Which is the last line, okay? And therefore, that completes the proof. Hopefully, you could see each step. And I know it might feel overwhelming, but as you practice it and sort of internalize a little bit, like a puzzle, what can I use? And I should say, purposely, I use this software because it tends to give you the most complicated problems, not the easiest ones. Okay. Not as complicated as you would get on an exam. So R or N, then, both Q and F. If B, then N. G or B. If G or N. Q or T. Okay, so Q or T. Right? Well, what would give us an or? Well, a disjunctive syllogism actually would help get rid of an or, process of elimination. So we could get that by addition. So we can get Q on its own line, we can get T, Q or T, just by adding. So we could try for that. Do we have any Q's? We have Q there. And then if we could prove R or N, right? So it looks like we're going to have to use a constructive dilemma. But do we have that? Not yet. Okay, so it's going to be either constructive dilemma, right? Or addition. Is to get to that. Our last step is going to be one of those. So what do we write on line 5? What can we know, right, from just these? Okay. Well, we don't know what Q and F are because we don't know what R and N or N is. We're not told that that's true. We don't have a hypothetical syllogism, right? Right? We could combine by conjunction if P if B then N and G then R by conjunction. We can combine any of these actually, right? So let's see if that's it, right? But they're going to go for, of course, if G then R and B then N. Why? Because we're going to need to get to B then, and B then N. Why would we need to do that? Because that is going to give us the G or B that's here, and then we're going to need to know R or N, and then by simplification, okay, so we go here. All right, so let's just combine. That's something we do know. All right, so what's now something we can learn from the above? What do we write on line 6? So we have these two, right? And if only we could, let's see, we got these two, right? We're not going to go if G then R by simplification, because that's already given to us. We're not going to do R or N by constructive dilemma. Why? That doesn't follow. Because we don't have, does it? G or B? Oh, R and N. Yeah, R or N follows by constructive dilemma. So we know that. So let's do that. That's something we do know. Do you see that? If you just reverse that, put that down there. G or B, true. Therefore, we know R or N is true. Put it down. We know it. Okay, good. So now what do we write on line 7? Okay. If we know R or N is true, we're going to know that Q and F is true. Right? And now we're getting closer. We're starting to paint ourselves in a corner, which means a good corner where we know what the conclusion is. If we know R or N is true, then we know Q and F is true. If we know Q and F is true, then by simplification, we know Q is true. And we know Q is true, we know Q or T is true just by addition. So let's first work out the modus ponens, R or N, therefore Q and F, right? So if P then Q, this is in the P position, this Q position, P, therefore Q. Well, sorry, that's confusing if I do it that way, but you know Q and F is true. Okay. Simplification, let's do Q. Get it on its own line, and now by addition, Q or T has to be true. Again, we said it was going to be either addition or constructive dilemma. Well, we did have to use constructive dilemma, but it ended up being addition that got us there. Again, always just put down what you know. What can I guess? Not guess. What can I know from the above? Okay? Okay, so Q or T, that's our conclusion, by addition. Okay? Right? If Q is true, Q or T has to be true. Okay? That says now turn to the exercises in your book, which should be the case. And you'll find them a little bit easier to build upon in your homework. it would be best, as I've probably said before, if you try to read through the chapter before you listen to the lecture, and then go back in, and hopefully it makes more sense to start doing the problems and so on. If you want any help with any of the homework questions, or feel stuck anywhere, obviously you can feel free to meet with me either virtually or in person during my office hours. The second thing I would say is, and if you need answers to specific homework problems, do let me know, and I'm happy to provide them. Okay, so thank you very much. We're going to exit this, and I'll see you next time.